All right. Hello, everybody. I'm Carolina Lima. I'm a PhD student, actually a PhD candidate at this point. Um, and the course that I'm going to talk about is going to be Unruh with particle detectors and applications. I have written my email in this chat, so if you have any question, just write to me. And so the topic that we're going to cover in this course is related is within the field of relativistic quantum information, what I call RQI, we generally call RQI. And just a brief overview, RQI, the way I would describe it would be the intersection between information theory, relativity, and quantum mechanics. And if you ever go to a conference in RQI, you're going to see that it's a very diverse research field. You can see pretty much anything you imagine. You're gonna see some people that work on QFT in curve space. You're gonna see some people discussing algebraic QFT or axiomatic QFT. You're gonna also see tabletop experiments for quantum gravity, like GIE, for instance. Quantum thermodynamics, semi-classical gravity, and the limits of semi-classical gravity. People talking about quantum reference frames and or quantum to classical transition, some philosophy of physics. So you're gonna see pretty much everything that it's really extensive. Um, so here in the course, in this course, and in my particular take of RQI or the group that I participate in, mostly studies QFT in curve space. And we add some concepts from quantum information theory. So that's our part of RQI. And today, the lecture today was based mostly on Barrow and Davis, that book, the very canonical book, and also on some lectures that I attended by Sergei Sibirikov at Perimeter a few years ago, which is called QFT in Curved Spacetime. And the recordings are on PIRSA, like the Perimeter website that contains the most videos, most lectures, most seminars at Perimeter. So let's get started. And if you have any question, just you can interrupt me. You can also ask in the group chat. And as I said before, you can email me if you don't want to ask directly. I'd say we're gonna go slowly. We'll open a lot of calculations because I have the impression that sometimes people don't show the details. And when you try to do yourself, especially as a master student in the beginning, it is a bit hard. So I'll just try to hopefully help your life a little bit. So, okay, let's get started. So, QFT, in space, the basics. Okay, so we're gonna start with a classical field theory. And well, first of all, I need the ingredients that I required. I need a globally hyperbolic background manifold. Endowed with symmetric tensor. G mu and u. And I know that in most of the times when we see QFT, the signature convention is going to be mostly minus, but I will actually, my convention is going to be mostly plus. Conv, yeah, convention. Okay. Um, and so just so everybody's on the same page, globally hyperbolic means that it admits a foliation of the spacetime. In Cauchy surfaces. And the reason that this is important is that under this condition, we have a well-posed Cauchy problem. Okay, so to this background, we are going to add some matter. So let's start with the action of a free real scalar field. A free real scalar field in this background manifold, right? Okay, so I can write the action as just the integral. I have n dimensions here of this Lagrangian density. And here the Lagrangian density is going to be given by minus a half square root of minus g times g mu nu partial mu plus m square y square. So here I have minimally coupled model, right? So just again that everybody's on the same page, just a reminder, this is the determinant of the metric. Okay. Well, so we can write the other Lagrange equations, right? Equations. So partial L partial phi equals to partial rho of partial L partial rho of L of phi. And then the left-hand side is gonna give us minus square root of minus, yes. Is this a question? Maybe not. And then the right-hand side that is gonna be give us minus partial rho of square root of minus g, then g mu rho partial mu of phi. Okay. Now if I just write the whole the Lagrange equations, what I have is minus is gonna be 1 over square root of minus g times partial rho of square root of minus g mu rho partial mu of phi equals to m square phi. And if you notice, this is just the Dallon version for the metric g of phi. So this is the same as partial Dallon version of phi minus m square. Dallon version of minus m square over phi. Yes, equals to 0. And this is a Klein-Gardner equation, right? Right? So far, so good. If not, just interrupt me, please. Okay, so now we must solve the Klein-Gardner equation, right?
Caroline,
Yeah.
Luis Dias Jimenez asked a question.
Ah, okay, sorry. Yeah. Am I going too fast? I was thinking I would go to maybe to. Okay. Is this good? Can you guys? So this is the Lagrangian density. Okay. That is the whole Lagrangian density here. Maybe I just because if I keep scrolling down to be able to write, then maybe it just shows too fast. I can also put this maybe to the side so it shows a little bit more. Yeah, so just as a review, so this was the Lagrangian density. And I just wrote the other Lagrange equations, which were I computed the left-hand side, the right-hand side, and then what we found is that it's just the Klein-Gordon equation, okay, for this particular metric. Okay, so please interrupt again if you need. So now we're gonna solve the Klein-Gordon equation, and to do so, we need to first, well, yes, choose a space-time foliation. Okay. So what we have here is like suppose that we have these foliations that we assume we do because of the global hyperbolicity. And I'll have some natural direction for this time, for this t, right? Say it's this. And then I have some normal vector here. So this normal vector here is the future pointing. Um, wait, unit normal vector to sigma, to this quantized sigma, okay? And here I'll have, in sigma, I'll have some induced metric, right? Induced metric, which I'll call G sigma. And G sigma of mu nu is given by G mu nu plus N mu N nu, okay? And now, in order to solve this equation, we need to define the Klein-Gordon scalar product for the solutions. Okay, right. So the way we're going to define this is the scalar product between phi 1 and phi 2. It's going to be minus I uh, times the integral along this Cauchy slice. And then I have the normal vector and the measure of the integral here. And then I'll have phi 1 partial phi 2 star minus phi 2 star times the partial of phi 1. Okay, so this is the definition of this Klein-Gordon scalar product. And I'll leave as
The,
an exercise.
the vector and mu It's contracted with the partial derivatives.
Yes, yes.
Okay, okay.
Yeah, exactly. Um, yeah, sometimes it's easier when we have like some metric in the ADM form, especially if it's block diagonal, because then it's just along this T component. But yeah, you can think of in the end you're contracting, so it's along the that direction, right? Along
Right.
the direction, yeah, the design. So, oh yeah, I was gonna say that I'll leave as exercises for you guys. But you can always write me if you don't know how to solve any exercise. If you try and it doesn't work, you can show me what you have done. So the exercise is show the Klein garden scalar product satisfies the following properties. So one, it is independent of the choice of Cauchy slice, which is really important. Two, if I take phi 1, phi 2, this is the same as the opposite order, but complex conjugated. Okay. Then three, um, the scalar product of phi with itself is not positive definite, meaning it can be negative as well. Fourth, phi 1 star with phi 2 star is also equal to minus phi 2 phi 1. Then phi with phi star gives you 0. And then uh, see that we have distributive property, but it is it's going to be linear in the first argument. So I have C1, phi 1, and phi 2 plus C2, phi 2, and phi 3. And then it's going to be antilinear in the second argument. So if I have phi 1 with C2 phi 2 plus C3 phi 3, that is going to be equal to C2 star phi 1 phi 2 plus C3 star phi 1 phi 3. Okay. Okay, so this is the end of the exercise, which is, I recognize it's a little bit long, but it's not that hard. So what we have is that there exists a complete set of mode solutions ui of x, which satisfies it's going to satisfy the scalar product between u I and uj. It's going to be just delta ij. Between ui star and uj star is going to be minus delta ij. And then the scalar product between ui and uj star is going to vanish. Um, and we're going to call these ones the positive frequency modes, whereas these ones are the negative frequency modes. And you probably notice now that I'm using ij discrete here. So here I and j are discrete, and probably you're used to continuous, but basically the continuous case is going to be analogous. Continuous case is analogous and is somewhat standard to present in the discrete case. So I'm just sticking to the literature, but as I said, it's straightforward to generalize. And okay, so with this complete set of mode solutions, I can write phi, right? So we can write phi in this basis. So I'm going to write a summation of I of AI, some coefficient times the positive frequency 1 plus another coefficients, AI star, times the negative frequency 1. Okay, so for now, these are coefficients. So this, they're just coefficients. Okay. And then finally, I can write the canonically conjugate momentum. And that is gonna be given by partial of the Lagrangian density along partial t of phi. And in this case, what we see is that the result is going to be this determinant of the induced metric times nu contracted with partial phi. Okay. And well, so far everything is classical, and then finally we are going to quantize. So I'm going to proceed with canonical quantization. Right. So basically, I will define some counterparts, the quantum counterparts of phi and pi, and then impose some equal time canonical commutation relations as it is usual, right? So I'm gonna impose um, equal time canonical relations for this quantized counterparts of phi and pi, which I will call phi hat and pi hat. Okay. So this canonical commutation relations are gonna be so phi at some time in position x with phi at time in another position is equal to the commutator of phi at some time and some position, and at the same time in a different position that is going to vanish, right? And phi at some time and some position, and phi at the same time in some different position in general. It's going to give you the I times delta n minus 1 of x minus x prime. Okay? And so how we're going to write this quantized field, we're going to write it as phi of x is going to be given by just what we had before. Remember that we had something like this. And now I'll just promote these coefficients to operators, right? As usual. So this goes to a hat, and this is going to actually be here, a head dagger. Okay. Now let's notice the following. Um, we have that the scalar product between phi and u1, this is going to be equal to minus I, and then uh, integral over the Cauchy slice of n mu, and then Tn minus 1x, and then linked to symmetric determinant times, now I have phi here, right? And then partial of ui star minus ui star partial of phi. And then I can rewrite this as minus I times this integral over dn minus 1x of n mu square root of g sigma times phi partial mu of ui star. But now, can someone tell me what do I have for this other term here? If I look at this part, and then look at this. Do you remember? Or am I going too fast? Maybe I'm going too fast. So let me just scroll down a little bit. Remember that we had the canonically conjugate momentum defined here, and what we had was this. So if you notice, I have this determinant of the matrix, square root of the determinant of the matrix. I have n mu here, and I have the partial mu along phi here, the quantized version. So what I have there is just u I star here times the quantized version of the quantity, which is just pi hat. Okay? But also, I have that if I take phi with u1, I can write this as expand phi just as I had before, just as I had here. Okay? And that will give me summation over j of a j hat uj plus aj, why is not j, head dagger ui dagger with, oh, it's j, with ui. Yeah, everything is J here. I think the way I wrote sound weird, but in the first entry, everything is J. The second one is UI. And what I have here is, if you remember that the scalar product between the UJ star and UI is going to vanish anyway, so the only term that contributes here is going to be this one, and that is going to give me a delta ij, right? So what I have here is just AI, right? Now, similarly, please interrupt me if you don't understand, okay? I'm just opening up the all this calculation so that you guys understand. If you feel lost, you should interrupt me. Um, Now we're gonna do something similar, which is to find the conjugate ones. So
Caroline,
yeah,
I have a question. It's more like a simple one, but the tangent vector and mu, it's not quantized because it's tell about the space-time or not.
yeah,
I
it's not quantized. Yeah,
okay.
you're right. Yeah, good. Thanks for your question. Um, Now, okay, similarly, I'll do some similar procedure just to see that if I computed the one between phi and UI star, what I would get is I, the integral over Tn minus 1x times n mu square root of g sigma times phi del mu of ui minus ui phi, and then also similarly, you can see that this is going to give you some AI dagger. Okay, so what are we going to do now? We're going to use those relations to find the canonical commutation relations for the ladder operators, for creation and annihilation operators. Okay, that is the idea here. So using those, we're going to get that if I want to compute the commutator between AI and AJ dagger, what I have is I'll just copy whatever I had for AI here, so I know that this is the same as that, right? So it's going to be minus I integral Tn minus 1 x. And here I'll write explicitly x and x prime, otherwise we may get too confused. So I'm going to write here as n mu of x times the metric written in terms of x. Then phi of tx partial mu of ui star, that's what we had, yeah, of x as well, uh, minus ui star of x times pi of tx, and then not getting used to the to the toolbox on the right, I'm sorry. Um, so here, yes, that's what I had, and the commutator of that with I times the integral g minus 1 x prime here, and that is going to be eta nu written in x prime, and then this also is a function of x prime, and then phi of t x prime, partial prime of nu, right? And uj, yes, uj of x prime minus uj x prime phi of t x prime. Okay, so let's have a look into this. We know that, let's look into this first term here and this first term here. So the commutator of phi and phi, we know it's going to vanish, so this term is not going to contribute. Now we're going to have this another commutator here that is pi with pi as well, which is going to vanish. And then finally, we're going to have terms like the cross terms. These terms are not, they are the ones that are not going to vanish, right? So this phi with this pi, and this pi with this phi. So let's try to write that. So I'll just pull out this minus I times I, so it's just 1. And then I'm going to write the integrals outside, x and dn minus 1 x prime. And then let's see what we still have. Oh, I can still pull out the things and just leave the operators. Okay, let me just write then. Um, okay, let's focus on one, then the other. So see this first one with this other one here. So that is going to give me a minus coming from the second term and mu of x times, let's see, mu of x times square root of g sigma of x. And then we have a uj of x prime and this partial mu of uy star of x. And then finally the commutator, right, between phi of t x and phi of t x prime, right? I think that's all correct. And then the other term is going to be, please point out if I find if there is any typo. Okay. And then now let's focus on this other term here. So for this other term, I also have a minus, and I have a eta mu of x prime. There's also g sigma of x prime. And then I'll get a ui star of x times partial prime of mu uj of x prime times phi of tx and phi of tx prime. Okay. Now, we know that this one is gonna be, maybe I'm just gonna open up a little bit of space. This one is gonna be I times delta of x minus x prime. And this is just gonna be the negative of that, right? Minus I times x delta of x minus x prime. All right, so if we, because we have this delta, let's just integrate over the x prime variable, right? So then let's see, I can write something here. So I'll just get rid of the one for x prime, I mean. And so I have this in the first term is going to be minus eta mu. Now I'll just suppress the x and x primes because I already, I already integrated over the x prime, so I will suppress some x in the normal vector and in the determinant of the metric. So I'll just write this, but you know what I mean. And so what I get here is just uj of x, partial mu of ui star of x. And then this other term is going to be plus, right? Plus, and I forgot an I. Okay, there's an I. I forgot an I from both, yes. And then that's going to be a plus times, yeah, this, I can actually pull this out. Let's see, put this out and put this minus here. Okay. Yes, pull this out. So I'll get minus uj partial mu of ui star plus ui star of x um, partial mu now of uj of x. Okay, so do you guys recognize this already? Or at least almost recognize this? So if I just take out this minus sign here. So if I put minus sign here, and then I remove this minus, and this plus goes to a minus, what does this look like? Any guesses? No guesses? Um, um, okay, so let me just copy something that I defined before. This here. If I just copy the definition here of the Klein-Gordon product, now what does this look like? Is it a bit more clear? This is some scalar product, right? So this is going to be the scalar product between uj of x, right? Which is doing the same, is exactly in the same position as as phi 1 here. And then with ui of x. And we have seen before that this is just delta ij. Okay, I'll just erase this now. But I hope it was clear that this was another way of writing just the inner product between uj and uy. So what we concluded? Just writing again. So it means that the commutator between ai and aj star is delta ij, as we expected, right? That's um, that's a canonical commutation relations when imposed to the ladder operators. Now I have another exercise uh, for you guys. And the exercise is using the same idea. Uh, show that the other ones, right? So A and AJ is gonna be the same as if I have A dagger I, A dagger J, and it's gonna be 0. Okay, it's basically the same idea that we did before. It's just if you follow the same idea from this, just use the same relations that I defined before, you're gonna find that. Okay. But again, if you cannot solve for any reason, then just let me know, okay? Then we're gonna um yeah, help each other. I can help a little bit and then you can perhaps understand how to do it. Okay, so all right, so we discussed all of that, and with those we can um define a notion of vacuum and a Fock space. Okay, so if I act with the annihilation operator over this vacuum, I must get a 0 no matter what kind of mode, which mode I'm using. So for ever I. And to construct this Fock space, well, I have a 0, like right a vacuum. And then if I act with creation operators on this vacuum, I'm gonna create a state with one particle, two particles, and so on and so forth. All right. Now, one important thing of the lesson today is that this notion of particles is ambiguous. Okay. And let's try to understand why, right? So notice the following. We can choose another complete set of modes as well, not only this one. So we can choose another complete set of modes. Okay, so I will write phi as a function of this new set of modes. So I can write phi as summation over j, and now my new annihilation operator I will denote with this tilde, meaning this is not the same as the one before, okay? This a tilde is not the same as a hat j, and then the mode u tilde j plus the creation operator a dagger j times the u star j. Okay. And because we have this other complete set of modes, we also have some associated vacuum to this new set of modes. We have some associated Fock space to this new set of modes. So let's write this down. So we have some associated vacuum. And this associated vacuum um, is such that if I act with this annihilation operators over this new vacuum, 0 tilde denoted here, it's also going to be 0 for every mode that I act with. And the associated Fock space can also be constructed by acting with these new creation operators into this vacuum, this new vacuum. So I can act with something like this, and so on and so forth. Okay, so that begs the question, what is the relationship between those two, right? The relationship between the two set of modes, the relationship between the two vacua, the relationship between the two Fock spaces. So, what is the relation? Well, since both modes, both sets of modes, right? Sets of modes are complete, we can expand one in terms of the other, right? Okay, so what I'm gonna do now is exactly that. So this U tilde, I will just expand in terms of the old modes. So alpha ji times ui plus some beta ji of ui star. So this is the new mode in terms of the old modes. Okay. And well, I can just take the conjugate of this equation. So I can just write this as, well, I can use black. This u to the star can be written as simply alpha j I star ui star plus beta ji star ui. Okay. Um, Now I want to also be able to write the old in terms of the new modes. So old mode in terms of the new modes. And then I can write the following equation. I can say that ui is equal to the sum over j of the scalar product between ui, uj along uj tilde minus the scalar product between ui and uj tilde star along uj tilde star. And I guess often it's the case that people get confused about this equation because I think we get a little bit used to, in quantum mechanics, the order of this product would be inverse from what is written here. So most of the times you would think of like, I would take, to get this coefficient, I would take the inner product between uj tilde with ui along uj tilde. But the reason for this to be the opposite is that the way that we define the Klein-Gordon the Klein-Gordon scalar product is the opposite of the usual quantum mechanics one. So basically, in other words, the first argument here is gonna be the linear one instead of the second argument. And generally, when we define in quantum mechanics this inner products, we're gonna use the second one as the linear and the first one as antilinear. So that's why the convention is such that we have to swap the order.
Is there a
But
special reason for that, or is just a convention?
it's a convention, but to be honest, I have also seen some, yeah, checking the like notes for to prepare this course. I have seen in at least one note that they define in a way that is actually linear in the second and antilinear in the first. So in that case, we would swap this order. So I think it's just a convention, and I follow the Byron Davis
I see,
book,
thank you.
and I think it's more standard, but. Um,
Okay.
Okay. Rodrigo, we're gonna get there. Okay. But thanks for the question. So, well, I mean, but well, in some sense, I'm also discussing this right now, right? I'm saying that well, I have one set of modes, and then I'm saying well, maybe I can find another set of modes that are complete as well. And then I'm expanding principle. I have two sets of modes, or even more, right? I can choose two sets of modes, and then I'll see the relation between them. Um, right. So we're writing the old mode in terms of the new mode, so we can just compute those two, and then we're good to go, right? So let's do that. So we have the UI with uj star, and to do that, I will expand uj. They'll just use this equation that I have here for the expansion of uj tilde as a function of ui. So I'll get ui with summation over k of, let's see again here, alpha jk uk yes, plus beta jk uk star, right? And then I don't know, to help you remember how this is antilinear in the second argument, I'll just do one more step here. So I'll sum over k of alpha jk star, because again, this is a coefficient on the second argument, times ui uk star, and plus beta jk star times the scalar product between ui uk star. Okay, and this is gonna vanish, right? And then this is just delta. Wait, I did something wrong. Yeah. Yes, okay, that's true. This is just delta I k. So that is gonna give you alpha star of ji, right? And okay, so we computed the first one. Let's compute the second. So the second is ui with uj star. So again, this is just ui. Then I can just take the conjugate of this one. uk, right? And so that is going to give you summation over k of, again, as is antilinear in the second argument, I'm going to get alpha jk, then the scalar product between ui uk star plus beta jk scalar between ui uk, and that is going to give you just beta ji, right? Any questions on this? So rewriting the equation that I had here, this one is going to be ui is just the summation over j of a star ji times u tilde j minus, yes, minus beta ji times u j tilde star. And that is how we write the old mode in terms of the new ones. Okay, and of course, I can just take the complex conjugate of this equation and get the u star. It's gonna be a alpha ji u to the j star minus beta ji star u to the of j. Okay, and just so you know, this alpha ij, beta ij are called the Bogoliubov coefficients. Bogoliubov coefficients. Okay. And I will give you one more exercise. So this exercise is show that the Bogoliubov coefficients satisfy the completeness relations, basically. So we have sum over k of alpha ik alpha star jk, so I'm summing over the second, minus beta ik beta star of jk. That is going to be delta ij. Then we have summation over k. Now we have alpha star of ki alpha of kj minus beta of ki beta star of kj, and that is also delta ij. Then we have summation over k of alpha ik beta jk minus beta ik alpha jk, that is going to be 0. And finally, summation over k of, let me see, alpha ki star beta kj minus beta ki alpha star of kj, that is going to vanish as well. Okay, so these are the 4 properties that you guys should show. All right, so now we have these relationships between the set of modes, the new set of modes and the old set of modes. And I want to relate now the 2 sets of ladder operators, okay? So next we want to relate two sets of ladder operators. So recall that I had found that AI is simply the scalar product between phi and ui. And then I can rewrite this as, I'm gonna write phi in terms of the new modes. So this is gonna give me, I had the A2 that had J, U to the J, right? Plus the creation times U to the star J. Okay, so I have this this relation here. I just wrote phi in terms of the new modes. And okay, so what I get is the summation over J of A to the head J times the scalar product between U to the J ui, okay, plus, let me put a parenthesis here, plus A to the head dagger J times uj to the star and ui. Okay, so I have computed this first one already here. Let's see. we computed this UI u to the j, and here what we have is u to the j ui, so we know that I just need to take the conjugate of that. So this one is going to be alpha j I, and now the second one, u to the star j with ui. What we had here is ui with u to the j, so again I just take the conjugate. So this is going to be beta ji star, okay? And therefore, what do we find? This is going to be simply alpha ji times a to the hat j plus beta ji star a to the dagger j. Okay. So that's for the relationship between the previous annihilation operator and the new annihilation and creation operators. Okay. And based on that, we can also write that AI dagger is going to be simply summation of over J of alpha star Ji times the creation operator, right? Plus beta Ji times the annihilation operator, the new annihilation operator. Okay, so far so good. Let me know if you have questions. Okay, so now we want to write the new ones as functions of the old ones. Okay, so I want to get what is the new annihilation operator, and that is simply the scalar product between phi and u to the j. Okay, so now instead of expanding phi in terms of the new modes, I'm going to expand in terms of the old modes. So what is that? There's going to be just the summation over I of AI UI plus AI over I UI star, right? With this UJ. So now what we have is summation over I of AI scalar product of UI UJ tilde plus AI dagger scalar product between UI star UJ tilde. Okay, let's look into this. The scalar product between UI and UJ tilde, we already have, right? UI UJ tilde is just alpha star of JI. So this is alpha star of JI. Now this other one here, we don't have yet, so I can compute. Let's do this then. U star with U to the J. What we have here? U to the J. We have something like this. Let me just copy so that life is a bit easier. So we had that UI with, let's see. No, that's not the best. Let's see. No, it's best to get this one, right? Let's get this one. We had that ui with u to the j was this. So if I'll just replace this with this, the conjugate. So if I have the conjugate here, I'll have the conjugate here, which is going to imply that this is 0. And if I have the conjugate on this other one here, this is going to give me minus delta ik, right? So this is going to give me minus beta j, ji star. Okay, so that is the result that we needed. I'll put this maybe here on some box, I guess, so that it doesn't get too messy. And then, so we're just plugging this, which is gonna be minus beta ji star. Okay, so that is gonna give us final equation as summation of over I of alpha star ji times ai minus beta ji star times ai dagger. Okay, and now if I just take the Hermitian conjugate of this, that is going to give me the a tilde dagger. That is going to give me the summation over I of alpha ji ai dagger minus beta ji ai. So far, so good. Any questions? So one important comment here is that these relations between the old and the new ladder operators are known as the Bogleubov transformations. Okay. Okay, so one important comment here is the following. If we have, if beta ji is not 0, okay, if there is any, at least for one particular choice of j and I, if there is one beta ji that is not 0, then we have a creation and annihilation mix. Okay, so let's think of why. So, well, let's look into, say, the first one of them. I can write the old annihilation operator as this expression in terms of the new annihilation operator and the new creation operator. If I have the beta ji is just vanishing forever j and I, then what I see is that, well, this creation operator is just like basically reshuffling of the new ones, you know? So there's no mixture between this annihilation operator and the creation operator of the other set. So if this vanishes, well, I'm just basically reshuffling, and that's all right. But if this is not vanishing, at least for one choice of J and I, then we know that, well, what is supposed to annihilate that vacuum is not going to annihilate this new vacuum, right? And so on and so forth, like the other way around as well. So let's try to make this a little bit more concrete. Um, yeah, to make this a little bit more concrete, let's maybe compute the following. The expectation value of the number of U tilde j, so the new modes, um, which can be written as just the tilde creation times the annihilation. And we're going to compute this in the old vacuum. Okay? Just to see how this new set of creation and annihilation operators are going to act in this old vacuum. So this expectation value is going to give you, let's just copy that one. So a tilde j over 0, acting on 0. So I'm going to just write down this new operators, new letter operators, as a function of the old letter operators because I know how they act on the old vacuum, right? So I'll just go back here and basically copy. So I have this relation here, right? Which is exactly what I need. So there's going to be summation over I of alpha ji um, ai dagger. Let me put this away. Minus beta ji ai. And then I need to multiply this by the complex conjugate of this, basically, right? I can just write down this. So it's going to be the sum over k, just change the dummy variable. So alpha jk star, right? Then this is going to be an annihilation operator. And then beta star jk. And a k dagger here. And all of that acting in the old vacuum. All right, so now let's look into some um, basic structure so that we don't do more calculations than we need. We can see that if I act with this creation operator to the left here, this is going to kill the vacuum, right? So this is going to be 0. And similarly, if I act with this annihilation operator to the right, that is going to be 0 as well. So let's see what we have. What we get is that summation over I and k of, so I get just the minus beta ji here, and I get a minus beta jk star there, right? And then finally I have the expectation value of ai times ak dagger. And well, here I can just rewrite this as commutator between ai and ak dagger. So I subtracted a term here and I need to add it back. So ak dagger ai. But notice that this other term is going to vanish as well because when we act with this ai here on this vacuum, it's going to kill it anyway. So what we have in this is just gonna be delta IK, right? So what we have is just summing over K already. So using the delta to sum over K, what I get is just the summation of I of beta Ji times beta star of Ji, which is just summation over I of the norm square of beta Ji. So in conclusion, well, provided that beta Ji is not zero, right? What we have concluded is that the vacuum zero is not empty of this U tilde J mode particles. Okay, so despite the fact that basically what we've seen is that the two vacua are not the same, right? Uh, what is considered a vacuum for this set of modes is actually going to contain some particles for this other set of modes. Does that make sense? Do you guys have any questions? I think this is maybe an interesting part to ask your questions. All right. If not, let's make some comments. Okay, so just to make sure, I have said this before, but let's just write down so that you guys have it there. So if this U2 that J are a linear combination of UI alone, meaning there's no UI star doesn't enter in the expression for U to the J. So um, only positive frequencies modes are going to be part of this combination. So this is really important. Um, then the two sets of modes share a common vacuum state. Okay. Now, I guess this begs the question. So what set of modes is going to yield the best description of a physical vacuum? And this idea of physical vacuum, I guess intuitively, what we would think is, oh, a state that has no particles, right? So a no particle state. But I guess the lesson that I'd like you guys to take is that we must abandon this idea. So we must abandon this idea of the best physical vacuum. So, in other words, we need to specify the details of the measuring device used in this measurement. Okay, so you need to specify the details of the measuring device used in order to understand what would be the physical vacuum for that measuring device. So basically, in how it moves matters. So this how this measuring device is moving, especially if it's the distinction between inertial and non-inertial really matters. Okay. Now, in Minkowski space, um, we tend to think of just one notion, right? Um, and that's the reason for that is that all inertial observers agree on the notion of vacuum. Okay, so Minkowski space is somewhat special in the sense that all these inertial observers are going to agree on the notion of the vacuum. But that doesn't mean that in Minkowski, we only have one notion of vacuum. Because if you remember, or if you maybe you have heard about Unruh effect, for instance. So despite the fact that all the inertial observers agree on this notion of vacuum in Minkowski, um, an accelerated detector or device, measurement device, in Minkowski vacuum will see particles. So for sure, this accelerated detector is not going to agree on the notion of vacuum that all the inertial observers have for Minkowski. So despite the fact that everyone is in Minkowski, there's still like not there is no unique version, unique notion um, of vacuum. So there is notion of the vacuum is not unique even in flat space. Now, when we go to curved space, this situation gets much worse. So in general, curved spaces, uh, we may not have such a preferred notion of vacuum like we have in Minkowski. Okay, so now, given all the story that I just told you, um, I thought of maybe opening up a discussion for a bit, and please give your opinions. Why do you think that we need particle detectors? So if you guys wanted to pick up your minds, I would open your mics and talk a little bit.
Caroline, there is a question in the chat.
There are no general conditions. Um, well, no, that's not true. So there are yes, there are situations. I guess you're saying general conditions. What I can think of, um, if I have a notion of time like killing factor. This notion of global time, and then I quantize with respect to this same the same time like killing factor, then this beta is gonna vanish where I'm gonna use the same notion of vacuum. So similar to this is basically what happens in this situation for Minkowski. I have a natural notion of time, and then inertial observers are gonna agree on this notion of time, basically. That is like basically in that case you can find this time like killing factor. But I'm not sure like what exactly you meant by finding general conditions. Like more.
So I was wondering because if I understood correctly, if that beta coefficient is zero, then the annihilation operators are basically the same, right?
Mhm.
So I was wondering what kind of condition the space-time should have to that beta coefficient vanishes. Then, but I think I understand your point.
But
This
it's not
is
necessarily, no, it's not only of course there are some conditions on the manifold on the
yeah,
space-time, but there's also the condition on the detector itself, right? Like the measuring device itself. Like is it accelerating? Is it inertial?
I see. Makes
Um,
sense.
so there are the conditions on both. I agree with you that there are conditions on the space-time as well, but not only.
I see. Thanks.
I think the surprising part is exactly that in Minkowski, not everybody agreed. And I know inertial observer would not agree on this, which I think before you take a course on Q of Tinker space, there's some you don't think about that. It sounds like as if there was a unique version, right? A unique notion of vacuum in flat space, right? So okay, let me see. There's another question. Um, I'm not sure if I understand what you're saying. Are you referring when you say positive frequency, are you referring to one of the sentences that I wrote here? Let's see. Here? So if this is the case, okay. So if this is the case, let's see, let's go back a little bit. Okay, UJ, where's UJ here? So if I have the situation in which this beta Ji is zero, then this positive frequency mode that in the new set of modes is just a linear combination of this positive frequency modes in the old set of modes. So I'm just saying that this new positive frequency are reshuffling of this old positive frequency. So what it means is that at the end of the day, I'm not mixing creation and annihilation operators. So I'm not if I act with an annihilation operator in the vacuum, and I trans let's say if I'm acting with this new annihilation operator in the vacuum, and I rewrite this new annihilation operator um, as a function of the annihilation and creation operators of the old one, I'll see that I only have annihilation operators in the old one. So annihilation operators acting on old annihilation operators acting on old vacuum are going to just annihilate it. So in other words, I won't mix positive and if I don't mix positive and negative frequency, I'm not mixing creation and annihilation. So I just have the same notion of a vacuum. Is that clear? Sometimes speaking is even harder than showing equations. I don't know. But yeah. So do you guys have more questions at this point we can? Yeah, I'm actually thought of like, I mean, I could continue a little bit more, but I wanted you guys to give me your opinion and why do you think we need particle detectors? If you Oh, that's a thanks for the contribution, Alfonso. Um, yeah, I like your idea, Luis. Luis is saying, are the particle detectors a way to choose a vacuum? Yeah, as I said before, there is this the motion, the trajectory of this detector is going to matter for which is the preferred vacuum, right? Um, oh, that's interesting. I never thought about this. How far, Marcos? How far? What do you mean by how far? Like how many particles would be produced? Like more or less particles, or maybe that's the notion that you have. Yeah, I mean, in other words, I wanted you guys to have like an impression of like why we need them, right? Otherwise, there's no point in giving this course. Well, let me let
I was thinking that with far, I was thinking that you when you change your state, you have a notion of change a particular vacuum that you can construct using your state. I don't know.
uh
And
ca- can you say again? Let me see.
um, when you construct a vacuum, you initially use a preferred state. So when you have to when you change a state, like you go to accelerated state, you have if you construct another vacuum beginning from this state, you construct another vacuum that is in some sense, I don't know how, that is different from the your initial vacuum state. So I don't know if you can construct a inner product between these vacuum states. You have a notion of distance. I don't know.
Oh, I see. Oh, I haven't thought about that, about this notion of distance, but and that's interesting. Yeah, not sure if there exists one, but that's a I like the idea. That's interesting. Um, okay, so I will just give my take on why particle detectors. So first of all, I'll just say, well, based on everything that we discussed today, I would say this sentence that is particle is what a particle detector detects. And I think first time I heard this sentence, it reminded me a little bit of first time you see tensors that they say tensors are just objects that transform like tensors, and nothing really makes much sense at that point. But um, but here it does make sense, right? Because based on what we discussed, this notion of particles as Fock space, Fock as excitations, is observer dependent. Okay, so this observer dependent is key. So again, if I have a particle detector moving versus a particle detector static in the same space-time, they did not they don't need to agree in this notion of how many particles they observe, right? So now if we just count the clicks of a particle detector, at least we have a notion of particle based on that particle detector itself. Now, there are some other reasons, and one of that is, well, in quantum mechanics, we already have the measurement problem. Right? And which is basically this tension between projective measurements and unitary evolution. Okay. Now, in QFT, this gets much worse. So in QFT, this is worse. Because projective measurements, they are not compatible with relativity. They actually may lead to faster than light communication. May lead to faster than light signaling. I'm not going to discuss this in detail here, but I would suggest that if you guys are interested, you should look into the so-called Sorkin's problem. There's a famous paper by Sorkin, and then there's a lot of discussion based on that initial paper. And from the same research group that I am part of, there's Jose Paulo Gomez, who has graduated already, but he has worked a lot on this topic, and it's quite interesting to have a look. Jose Paulo Gomez work. And finally, what do we do in practice when we are trying to experimentally measure a quantum field? To measure a quantum field, uh, we couple it to some probe. So we're going to couple it to some other, oh, that is, to some other quantum system. And this other quantum system we generally call a probe. And then we're going to measure the probe, right? And then measure the probe. And if you want, this would be an operational approach. So we're gonna some operational approach to measure this quantum field. So these are the reasons basically that I thought of discussing of why we need particle detectors. And so tomorrow my idea is to start by introducing this Unruh DeWitt particle detector model, discuss a few features of it, and then start with some of the applications of Unruh DeWitt detectors. And well, that's what I had planned for today. And now you guys can ask questions if you have. Okay, I'll stop recording, and then if you guys feel more at ease to ask questions, I'll you can do so.
I was thinking about